yesterday we drew the Lewis structures. We didn't talk about geometry of the shapes. We're going to talk about that today along with bond angles. I gave you an extra chart because the one in your notes I didn't realize didn't have the bond angles. So we're going to utilize the one that I handed you today because it actually has the bond angles, and you do have to know the bond angles. Like it's Halloween or something. Things are going wrong. Okay. So some atoms, such as nitrogen and phosphorus, tend to share a lone pair because they had those lone pairs on their structures with another atom that is short for electrons. And this leads to something that we call a coordinate covalent bond. It's very common in Lewis acids and bases, which are the ones that are exchanging electron pairs, not protons. And so we're going to draw the structure for BH3, which is very simple, because it is 3 bonds, and that's what BH3 looks like. Okay, so clearly it does not have an octet because it is an exception to the octet rule. But what it can do is NH3, if we draw the structure for NH3, has a lone pair of electrons on it. So draw that structure, lone pair, and then has 3 bonds. And so what it can do is it can take this lone pair and it can donate it and share it with that BF3. So now you draw it joined up, which I will show you what it looks like. You basically join them together, make a bond between that where that lone pair was and the boron. And so now nitrogen no longer has the lone pair. So basically nitrogen is donating both electrons to share with boron. So now boron has its octet and nitrogen has its octet, and there's the 3D rendering of what that would look like. Okay, and that would be a Lewis acid base reaction. We don't do a lot of Lewis acid base, but I want you to recognize it. Okay, so that's going to bring us to polar bonds, polar molecules. If you remember from Chem 1, bond polarity and molecular polarity, 2 different things. Okay, so if we look at these 2 right here, we have water and ammonia. And we know that the oxygen-hydrogen is a polar bond, and we know that the nitrogen-hydrogen is a polar bond. So if I was going to draw those bonds just by themselves, I would draw the dipole that looks like this. Remember, the dipole is the unequal sharing of the electron, and so we draw the arrow towards the more electronegative because it's going to get the electron more. This is important, so pay attention. In pre-AP Chem, we told you, look at the structure. If it looks symmetrical, then it's nonpolar. If it doesn't look symmetrical, then it's polar. You cannot do that in here, okay? In AP, we tell things that so the masses can understand it in pre-AP. In AP, we got to say what's really happening, which is why the atomic structure didn't work out so well for some people because they're still using the same explanations we would have used in pre-AP. This is a whole different ballgame if you haven't figured that out by now, okay? And so we can no longer say, oh, it's symmetrical, so it's going to be nonpolar. No, we have to talk about the dipoles, and we have to talk about if the dipoles cancel or don't cancel. And so if I look at this particular water molecule, I've got 2 bonds, and my overall dipole is going this direction for the overall molecule because I've got the electronegative oxygen, and it's got 2 lone pairs, so there's more electron density, of course, that way. And then the bond itself, oxygen is getting the electron more than hydrogen. Okay? For NH3, overall bond is going this way. So that would be the dipole for that particular molecule. So those would be examples of polar bonds and also polar molecules. But there's often times where we can have polar bonds but a nonpolar molecule. Okay, so now we're going to draw the Lewis structures for methane, easiest one. Okay, and for carbon tetrachloride. Lone pairs. I mean, we need the lone pairs, but for this we actually don't to determine what we need to know. My dots are messy today. Okay, so CH4 has no dipoles at all. Okay, because the carbon hydrogen is a nonpolar bond. Okay, so there are no overall dipoles to draw here. So all polar bonds, it's a nonpolar molecule because it doesn't even have polar bonds. But the carbon-chlorine definitely is a polar bond, right? And its dipoles would look like this because chlorine is a lot more electronegative than carbon. So what I would do is I'm going to draw my dipoles like this, and I'm going to show that the dipoles cancel out. So although the carbon-chlorine are polar bonds, the overall carbon tetrachloride molecule is non-polar because these dipoles are canceling out. Because if I look, this is, you know, partially negative, all the way around. They cancel each other out. Okay? So you would say the dipoles cancel. Okay? Oh, wrong one. Okay. Some other examples of where you might have the symmetry of the molecule and the dipoles canceling. You can say, because of the symmetry of the molecule, the dipoles cancel. You just can't say the molecule is symmetrical. So there are certain things that you should just memorize the structure. And this one caught y'all in the beginning of the year. What is the Lewis structure of carbon dioxide? There are certain things that you should just look at and know how to draw them. Okay, dipoles would go this way. Dipoles would go this way, so they would cancel. This way. And if they gave you a molecule and they ask you to tell me the polarity, it is not a bad idea to draw the Lewis structure, draw the dipoles canceling out, and then say, due to the symmetry of the molecule, the dipoles cancel. If you just said the molecule is symmetrical, they're going to say, no points for you. Okay? Is this making sense?
So BF3 cancels out as well, right?
Yeah, because look, they're all going the same direction, right? Now, let's say I did this. I would have this going this way, this going this way, and this going this way. So those would not cancel. See? Does that make sense?
Yes.
Okay. All right. Then let's talk about, come on, lone pair. Oh, Vesper. I skipped a script. Vesper theory. Vesper theory is valence shell electron pair repulsion theory. And it's what governs the shape of the molecules. Okay? It's going to tell you that if lone pairs are on the central atom, those lone pairs take up more space and they shove those other atoms down a little bit. Okay? And so it's going to change the shape. Here is NH3. Okay? And notice how that lone pair takes up a lot more space, and so it pushes those other ones down a little bit further. Okay? So we're going to learn something different this time about molecular geometry. We're going to learn something called electron or electronic geometry. And so if you look at either one of the charts I gave you, the one in your notes actually shows it a little bit better way to understand it, but it's also listed on the one with the actual angles. Okay? So if you look at tetrahedral, right? Tetrahedral electronic geometry means it has 4 areas of electron density. So if I'm looking at this NH4 molecule, I have 1, 2, 3, 4 areas of electron density. Your lone pairs count as an area of electron density. So I would go and I would say that my electronic geometry here is tetrahedral because there's 4 areas of electron density. But because this is a lone pair, I go and I look at it and I say 3 bonded pairs, 1 lone pairs makes that shape what? Trigonal pyramidal. Okay? And what would the bond angle be on trigonal pyramidal? 107.5. Okay? For tetrahedral, which is the electronic it's 109.5. But because the lone pairs takes up a little bit more room, it shoves the hydrogens down a little bit, so it decreases the bond angle. Yes.
So. Okay, I got it.
Good talk.
Yes.
Okay, so we're going to draw the Lewis structure. We need to include the lone pairs and the bonding pairs, and we call those areas of electron density, or they call it electron groups, number of carbon pairs. Okay, so we're going to draw a few. We're just going to draw a few because you can look at a chart and you've got lots of practice to do. So before we actually draw one, we drew yesterday, if you flip back in your notes, we drew PCl6 minus. We drew it, so look at that. Or we could even do it without looking at it. It's got 6 areas of electron density, no lone pairs, so what shape would that be? Octahedral, okay? So we're not going to do that one because we already drew it yesterday. So we are going to do the ICl3 because that I'm trying to pick the shapes that I know are going to look a little bit different for you, so we can go through those. So ICl3, how many valence electrons do I have total?
28.
28. Okay. So I'm going to draw my central structure, right? And then I'm going to put all my lone pairs. Okay, how many electrons do I have there?
24.
24. So I need 4 more. So the only place I can put, what is our rules about Lewis structures today, when I have extra ones, where do I put them? Central atom. So I'm going to do them like that for now. Okay, so how many areas of electron groups do we have around there? Or you can also look at it as I have 3 bonded pairs, 2 lone pairs. What would that shape be?
It's trigonal bipyramidal.
So trigonal bipyramidal is my electronic geometry, because I have 5 things. But my molecular geometry is
T-shaped.
T-shaped. So I would actually redraw that to look like this. My dots look like they're coming. This is, there we go. Okay, so that's T-shaped. And what is my bond angle? 90 degrees. Okay? All right, let's do another one. Does everybody have that before I erase it? Yes?
Yes.
Okay. So now let's do BR5. Not BR5, BRF5. Knew I was forgetting something. How many electrons do I need?
42.
42. Okay, so BR in the middle. Draw my skeletal structure. Go give everybody their lone pairs. And how many electrons do I have here?
20.
I should have a lot more than 20.
Yeah. 30.
I should have a lot more than 30.
36. 30. 40. Wait.
40.
40.
Okay, I have 40, and so I need to add 2 more. So where do I put those?
Central atoms.
Central atom. So what is my molecular geometry going to be here? Well, that's my electronic geometries because there's 6 areas of electron density is octahedral. But I have one of those as a lone pair. Square pyramidal, right. So square pyramidal would be my shape. And, well, it's square. What do you think the bond angle is? 90 degrees. Now, let's also look at that. Is that going to be polar or nonpolar? Also, let's go back to that T-shaped one we did previously. Definitely polar. Okay. All right. And then I am going to do one more. I'm going to skip over and do the ICl4 minus.
So did we draw that one correctly? Like, is that correct? What you have
Yeah, that one's, yeah, pretty much.
close enough?
Close enough, yeah. The reason I wanted to redraw the T-shaped one is because the way we drew it, it looks nothing like a T.
Right.
But then when you truly put the two lone pairs and shove those things down, it's a T. Yeah.
Wait, so what? I don't get how it's polar. I know it goes to the most.
Because okay, so you see those lone pairs right there? That's going to make it polar. Because even though I could draw these like this, and I could draw all these, but I've got this lone pair taking up space that's negative. So you got to think of this as it's taking up this space around it. So these are shoved down, and so my dipoles would not cancel out because I've got this right here. I've got this blank space from the lone pairs.
So that's why iodine is also polar because it has.
Well, that one, if you looked at that T shape, this has got lone pairs right here and right here. So then those would be, let's see, it's going to be going this way because chlorine is more electronegative. But you've got these lone pairs taking up space that are negative. So it's not all in the same, it's not symmetrical, it's T-shaped. So pretty much on the T-shape, everything is the bottom half of that plane and not the top. Okay? And then we'll do one more, and then we got to move on if we're going to get through this. I didn't mean to do that. Okay, so let's do this one right here, ICl4 minus. As a matter of fact, I'm going to pause, and I want you to do it. So freeze that, pause this. Here we go. So you should have gotten square planar because you have 6 areas of electron density, which would make the electronic geometry octahedral, and then when you make 2 of those lone pair, it's square planar, also 90 degrees. Okay. All right.
Wait, why is it polar?
Because you've got this, this, and this, and this, and then you got lone pairs, lone pairs.
Okay.
Yeah.
What do you?
Did you not draw the single bonds on the left side of the thing, but on the right? You did like the single bond dashes to the right side?
I just forgot the bonds, yeah. Sorry, forgot the lines. They're there. Okay. All right, so that's going to take us to hybridization. I think I skipped one. Yeah, nope. Okay. So the current model of the that we've been talking about, the localized electron model, there is a problem with it. 2 problems to be exact. And that is, if we were to look at the orbitals, let's say for methane, CH4, if we were to look at those orbitals, we have a 2s orbital and a 2p as our valence electrons. We have 2 electrons in the 2s, and we have 1 electron in the 2p. So we would expect those to be at different energy levels, but we'd also expect them, hey, there's 4 things centered around there. You would expect it to be 90 degrees because there's 4 things around a center, and there's not. It's 109.5. And that is because let me show you. So if I have methane, so carbon is S, and then a P right there. So also if I look at that, it looks like, even though I know I have 4 valence electrons to share, I only have 3 empty orbitals, and I know that I'm forming 4 bonds. So basically what it does is it hybridizes, and it says, I'm going to take the S and the P, and I'm going to put them together in 4 equal orbitals, so that then I put my electrons like that, and now I have 4 equal, even, Steven bonding sites. Okay? It would not probably ask you to explain hybridization. It just wants you to understand how to recognize it. Okay? And so depending on how many bonds you need, we can determine the hybridization of the orbitals. And it's actually quite simple. Okay? We did not do this in pre-AP. Okay? This is part of the valence bond theory, which is an extension of the localized electron model. And it's just about hybridization. 2 atoms form when both of these conditions occur. There's an orbital overlap, so the orbitals have to get close enough to overlap, and the maximum of 2 electrons opposite spin can be present in those overlapping orbitals. But here's a handy-dandy little chart that we're going to show you in a second, okay? Because of these orbital overlaps, we have something called sigma and pi bonds. We talked about it a little bit yesterday, and I said, don't worry about that. I'm going to explain it tomorrow. But basically, a sigma bond is the overlap of two s orbitals and a p orbital, like head-to-head, like the orbitals are head-to-head overlap, okay? That's the first way any bond forms. All single bonds are sigma, okay? You have to have a sigma bond before you can have anything else. You've got to overlap head-on, okay? It forms the strongest possible bond because they're head-on. P orbitals are directional, and if you go back to p orbitals, the shape, okay, S looks like that, and then a P looks like that, right? So basically what happens in a p orbital is they do this way instead of head-on like this, okay? And so those blending of those orbitals we call hybrid orbitals. They have the same energy. So whereas an S has slightly lower energy than a P, an sp3 would be degenerate in that means they're all the same level. So it hybridizes them, overlaps them, okay? And on your paper down below, it's kind of showing you this forward and then the sideways overlapping. Pi bonds come from that sideways overlapping of the p orbitals, okay? It's the region above and below that the internuclear axis. They never occur without a sigma bond first. So you got a pi, you got to have a sigma. Okay, you can't have one, you can't have a sigma, you can't have a pi without a sigma. Okay? Carbon does this, and so do those CNOPs. All those things that can double, triple bond, they're going to have pi bonds as well. So let's look at this. That's kind of what it looks like. Okay? A single bond is one sigma. A double bond is a sigma and a pi. Guess what a triple bond is? A sigma and 2 pi. I would just say you got a sigma before you can pi.
So once you get one sigma, you can't have like two sigmas, right?
No, once I have a sigma is always just a single bond. But if I have a double bond, one of those is going to be a sigma, the other one's going to be a pi. If I have a triple bond, 1 sigma, 2 pi. But if it's just a plain old simple single bond, it's a sigma. It's convenient that they both start with S. Single is sigma. Here is a handy-dandy chart that can help you remember how many hybrid orbitals are present based upon how many bonds are needed. So if I only need 2 bonds, then it's going to just be an sp hybridization. If I need 3 bonds, it's an sp2. If I need 4 bonds, it's an sp3. Easy enough, add up your S and P's, and that's how many bonds you get. That's how many orbitals you have. The d orbitals no longer tested on AP exam. I have them on there so you could recognize them for trigonal and octahedral. You would use a D, and then in the octahedral you would use 2 Ds, but they will not ask you. That's no longer tested. It's beyond the scope of AP. They just ask for the first SP, S2, SP3. Okay. The bond order, we talked a little bit about that yesterday. We said if you have a bond order of 1, you have a single bond. Bond order of 2, you have a double. And bond order 3, you have a triple. You will find out today, when we get to resonance, that's not always an outright 1, 2, or 3. We can have a 1.5 bond. You can have 1.3 bonds. But if you notice, as you get double, triple, your bond energy is going up. Because now you're breaking, in a triple bond, you got to break 2 pi's and a sigmas. Okay. Resonance structures and formal charge. Okay. We did resonance structures in pre-AP. We basically told you sometimes there's more than one way to draw it. In the case of ozone, I don't know if that bond is between the double bond. I don't know if it's between the first and second or the second and third. So we have to draw them both ways, and we say they have resonance, and we represent it with the double-headed arrow, and we say it has resonance. Okay, that means those are both feasible structures. They're basically equal. We just don't know where the double bond is. Okay, in actuality, if I were to do measurements on the bonds, they wouldn't come out as a bond order of 2 and 1. Both bonds would come out to a bond order of 1.5. Because we're drawing this on paper to represent it, but in actuality, it's a mixture of a single and a double. Because it could be either way. So what determines whether that oxygen double bonds with the first one or the third one, so it is a mixture. In the case of carbonate, which is CO3 2-, there's actually 3 total resonance structures, all feasible. We would need to add in those arrows because they're all feasible, okay? And when we did the studies on that, we wouldn't come out as a bond order of 2, 1, and 1. All of them would come out to 1.33 because it's a mixture. Yes?
So if on like the AB test, it asks you to draw the Lewis structure for something like that, and you only draw one of them, is that okay?
No, they will, if they want your resonance, they'll usually say including all resonance structures.
Okay.
If you know it has resonance, I would draw it anyway.
Okay.
Yeah, for sure. Because that may be what they're wanting you to recognize. So if you know like this, and resonance is not going to show up on things that just have single bonds.
Right.
It's going to show up on something like this where how can you tell which one has the double bond? You don't know, so you have to draw them all. Or what they'll do is they'll give you a structure like this, and then they might give you like CO2 and say, hey, this one has a bond order of 2. This one's showing up as 1.3. Why? And then you would say because it's a resonance structure and it's a mixture. Okay, so that's going to bring us to formal charge. Resonance structure is when they're all equivalent possibilities. They're all feasible, they're equivalent, one's not better than the other one. A formal charge is used when you have many non-equivalent Lewis structures, meaning I can draw this several different ways. Which way is the actual right way? Because these several different ways all satisfy the way I draw a Lewis structure, but which one is right? And so the formal charge is a way that we can calculate that and figure it out. It might be a tad bit confusing. It might be today. We will practice it some more later. So today, just bear with me, okay? The formal charge is going to be the difference between the valence electrons, your non-bonding electrons, and your bonded electrons. And what you're looking for on a formal charge is you want the lowest possible formal charge on all elements, okay, in the structure. You're going to use this along with the following to determine the structures. You want the formal charge as small as possible, as close to 0 as possible. If it's an ion, the sum of the formal charges have to equal the charge on the ion, okay? And the molecule is most stable when any of the negative formal charges resides on the most electronegative atom, okay? All right, so we're here. You've got these two structures. We're going to calculate their formal charges. The formula for the formal charge is at the top of that page. I'm on, oh, there's no page number, so I don't know what page number. Find this, okay? At the top, you see atom's formal charge is equal to number of valence electrons minus number of bonded electrons minus half of the bonding electrons. Guess what half of the bonding electrons actually is? The number of bonds, right?
Oh, yeah.
Yeah. So formally it's defined as half the number of bonding pairs, but it's really the number of bonds, right? Because if I have 4 bonds, I have 8 electrons. 8 divided by 2 is, guess what? 4. Okay? So we're going to do these two structures. We're going to, first of all, I want you to predict which one of these structures is the correct way. If you were going to draw the structure, how would you have drawn it? On your paper, tell me left or right. Quickly, we got things to do here.
Right.
Right, so y'all say that, y'all are predicting that this is the correct structure. Prediction. Okay. We're going to calculate the formal charges on all the atoms. Okay? So we're going to, even though it's we're going to calculate the right one first because it's the first one on my paper. Okay? So we're going to start with the sulfur. Okay? Someone go get that, please. All right, so we have 6 valence electrons. Sulfur has 6 valence electrons, right? Okay, it has 6 valence electrons. In those 6 valence electrons, how many on the sulfur, how many lone pairs basically are on sulfur?
None.
So we're going to say minus 0. Okay, we have how many bonded electrons? 8. So 8 divided by 2, which is 4, means that we have a plus 2. That's already written on your paper. I forgot to mark it off. So that sulfur has a +2 formal charge. The oxygens are all equivalent, so we only have to do this one. I'm going to write OX. You don't think it's 0. 6 valence electrons. How many does each oxygen, how many lone pairs does it have, or how many total bonded, non-bonded electrons?
3 or 6.
6, okay. And then 2 divided by 2, which is 1 bond, gives me a -1, right? So this would be -1, -1, -1, -1, which is going to be a total of a -4, right? So when I add those up, my total formal charge for the whole molecule is -2, which it has to be a feasible structure because it has to add up to the charge of the ion. Okay? So now let's do this in red. Now let's do the other molecule. My sulfur now, I have still 6 valence electrons. I still have 0 non-bonded electrons. And how many total bonds do I have? 1, 2, 3, 4, 5, 6. 6 times 2 is 12. So 12 divided by 2, which is 6 bonds, is a 0 formal charge on sulfur. Okay? Now we're going to do the double bonded oxygen because it's going to be different. 6 minus 4, right? Minus 4 over 2, which is 2. And that gives me 0. Now we'll do the single bonded oxygen. 6 minus 6 minus 2 over 2 is -1. So these were 0, these were 0, -1, -1. So it still adds up to the charge of the ion. So based on the formal charge, this structure is actually better. So that would be the correct structure. Because I have more atoms with a 0 formal charge, and more importantly, my central atom has a 0 formal charge, which is better. So that's how we do that. Okay? But here's what I want to tell you first and foremost when we're calculating these. Does everybody have this written before I go to the next slide? Because this is what's going to be important. This sentence right here. Don't use it if they don't ask for it. Okay? This is a way to do this if they give you like multiple structures and say, hey, which one of these would be best? Calculate the formula charge and figure it out. But if they just ask you to draw a Lewis structure, you draw a Lewis structure that fits all the criteria and move on. Do not try to impress them that you know how to do formal charge and draw like 2 or 3 structures and do it. A, it takes up extra time. B, you might screw it up. So if they don't ask about it and they don't indicate that you need it, draw a proper Lewis structure and move on. Only use formal charge when they specifically refer to it or it's completely obvious that you need it. Okay? On a scale of 1 to 10, how dazed and confused are we with formal charge?
Wait, is 10 confused?
Yes.
Like a 2?
Okay. Then I did a better job. I fumbled a little bit during 5th period, which is why I wanted to re-record. Okay. So that's going to bring us to the end. Whoop, whoop. You can read, so I'm going to let you read through these. Also, you're going to watch those videos. Also going to be helpful. Remember, if it were me, I would be taking good notes. And then I'm going to leave you with this, because this is the most important takeaway for this unit from moving forward. Only because I can't use a stronger language. Draw the dang Lewis structure. If they're asking you a question about bonding, about behavior of bonds or behavior of molecules, draw the structure so you can see, is it polar? What kind of intermolecular forces is it going to have? What kind of angles? What kind of this? Draw the structure. Okay? And that's where I leave you today.